I'm Tom Fetter, and my project is using black powder for parachute deployment. I pride myself in having a high success rate launching and recovering rockets. In fact, I track the outcome of all my flights in a spreadsheet. So I was concerned when two new rockets experienced recovery failures, each on their second flights, both failures on the same weekend. What was different about these two rockets was they used recovery blankets rather than the pistons that I had mostly been using on previous rockets. I had always used the online black powder calculators to determine the amount of black powder, and that had worked for the pistons, but I needed to understand the reasons for these failures before flying these rockets again. Do chute protectors require more black powder than pistons? Do black powder calculators underpredict the amount of black powder required? Was there a problem with my black powder? The black powder I used was 20 years old. Is there a shelf life for black powder? There are many online black powder calculators, and all give the same answer because they can all be traced back to the InfoCentral website calculator. In addition to the calculator, the InfoCentral page gave the equation that was used to calculate the pressure, and it gave the values for the constants that were used in the equation. But what it didn't show was the black powder chemical reaction equation used to derive those constants. What is black powder? Well, it's a combination of potassium nitrate, saltpeter, sulfur, and carbon usually in the form of charcoal. And when combined in these proportions, it's known as the traditional or Waltham Abbey formula that dates from the 1600s. The GOEX safety data sheet gives a range of weights that matches this formula. And Chevreul's equation, which is the most cited of the black powder chemical reaction equations, also fits the formula as well. And the combustion products of Chevreul's equation are potassium sulfide, a solid, carbon dioxide, and nitrogen. And it's these two gases at the temperature of combustion of the black powder that produces the pressure that deploys the parachute. Now, there's actually four equations that are commonly cited. They all date from the early 1800s. It's the heyday of black powder. They're all balanced equations, and each one has an increasing number of combustion products. We're going to start with Chevreul's equation, but then we'll loop back on all four. How do we calculate the pressure from these equations? Well, we start with the ideal gas law, where P is the pressure, R is the universal gas constant. That's the amount of energy that's required to raise a certain quantity of gas by a certain temperature. T, which is the absolute temperature of the gas, and in the case of black powder, is the temperature of combustion of the gases, which is about 2,800 degrees Fahrenheit. V is the volume in which the gas is contained, and N is the is the quantity of gas measured in moles. Now, to calculate the number of moles of gas, we use the molecular weight of the gaseous combustion products, which is calculated from the individual components from the particular equation that we're using, in this case, Chevreul's equation. And for Chevreul's equation, the molecular weight of the gases is 67.6 grams per mole. And from that, we can calculate the number of moles of gas from the starting mass of the black powder. Now, the InfoCentral equation, pressure equation, is stated in terms of a quantity called the gas-specific gas constant, which is simply the universal gas constant divided by the molecular weight of the gases. But these are the same ideal gas law. Now we can use this relationship to calculate the molecular weight of the gases that they're using in this equation, and it works out to be 69.74 grams per mole. Now that's not exactly the same as Chevreul's equation, but it's very close. So we have a model for calculating the pressure. Now we need to do some testing to verify this model. So to do the testing, I built a pressure chamber from a piece of 4-inch diameter, 12-inch long PVC pipe. It has a Honeywell commercial pressure sensor on it, which has an analog output. And to record that output, I built a Arduino-based data logger that plots the pressure real time and also logs the data to a micro SD card so that you can later pull it into a spreadsheet and plot the results. And running the first test of a 0.5 gram of black powder, you can see the blue trace here, we measured an initial pressure of 25.26 psi, and as the gases cooled, the pressure dropped to 1.2 psi at ambient temperature. Now, the black powder calculator model predicted 6.63 psi, the red trace here. So we can see that the calculator actually significantly underpredicts the amount of pressure that we measured, which was a surprising result. I ran the test 7 more times for a mean of 28.5 psi and a standard deviation of 4 psi. That large standard deviation is one of the many reasons that black powder isn't used commercially today. I also measured with both old and new black powder, and there's no significant difference between either one. So the old black powder was not the reason for the failure to deploy the parachutes. But clearly there's something missing from the black powder calculator model needed to account for the higher pressure. Now, the black powder reaction is exothermic. That means it gives off energy, and we can calculate the amount of energy that's released by using the enthalpies. The enthalpy is the amount of energy that's stored in the molecular bonds of the products of the black powder. And if the net energy in the ending products is less than the net energy in the starting products, then the equation is exothermic. And a half a gram of black powder produces about 1,000 joules of energy. Now, that's more energy than is needed to raise the combustion products to the temperature of combustion. And where does all that energy, excess energy, go? Well, it must go to either heating the air in the chamber or the walls in the chamber. Now, we're going to make the assumption that initially it goes to heating just the air in the chamber, and then as the gases cool, that energy is re-radiated to the walls and warms the walls of the chamber. And we're going to verify that against some measurements. So if we're going to add the heating of the air to the model, the pressure model, we need to add 3 steps. The first one is to calculate the number of moles of air in the chamber, and we use the ideal gas equation to do that. Secondly, we have to calculate the amount of energy that's generated. We use the enthalpy to do that, as we just seen. And the third step then is to use that energy to calculate the temperature of the mixture of gases using the specific heat at constant volume of the gases. And when we do that, we determine the temperature of the mixture of the combustion products and the air. We then use that temperature in the ideal gas law, along with the additional moles of air that are in the chamber, to calculate the pressure. And if we do that for the 4 equations that we looked at earlier, we see that 2 of the equations, Chevreul's equation and Berthelot's equation, both underpredict the pressure that we measured by a little bit, and 2 of the equations, the Abuse's equation and Cast's equations, overpredict a little bit. But you can see that all 4 of these are much closer than the original black powder model. Now, which of these equations is the right one to use? Modern analytic techniques show that black powder combustion consists of a number of intermediate reactions. And so the reaction overall is probably a mixture of all 4 of these equations, plus probably some others. But because Chevreul's equation does the best job of predicting the final ambient temperature pressure, and because it underpredicts rather than overpredicts, it's better to underpredict than overpredict the initial pressure. And the fact that it's the simplest of the equations, that's the one that we're going to use going forward in the model. So now we have a model that predicts the measured pressure, but we still don't know why there were deployment failures. We need a test fixture that more closely resembles a rocket. And that test fixture will include the shear pins because they're going to determine the force that needs to be generated by the black powder to deploy the parachute. So we need to calculate the shear strength of the shear pins. To do that, we use the shear strength of the material, which is available on any materials website, in this case, nylon. Then multiply that by the cross-sectional area at the minimum diameter of the screw. And that gives us the shear force needed to shear the shear pin. And the number that we get from that equation, that calculation, agrees very closely with the test results for shear pin strength from Damerou's extensive rocket materials testing website. So the deployment fixture looks very much like a rocket. It consists of a parachute tube with a rear bulkhead coupler that remains permanently attached during the test, and a front bulkhead coupler that approximates the nose cone that's attached with shear pins. And the enhanced model tells us that a 1/4 gram of black powder would be necessary to shear 6 number 256 shear pins, whereas the original black powder calculator said 0.93 grams would be necessary. In doing the test, we see that 0.15 grams failed to deploy the nose cone and 0.3 grams energetically deploys the nose cone. So these two numbers bracket the amount predicted by the enhanced model. That validates the pressure chamber test and the enhanced model, but it still doesn't explain the deployment failures. There's still one missing piece. And if it isn't obvious by now, that missing piece is the parachute. So for this next set of tests, we're going to actually include a parachute in the parachute tube that fills the parachute tube. Now, this particular test fixture for this test set of tests is the same size as one of the two rockets that had experienced the deployment failure, TR1. And in this rocket, there are two 256 shear pins. And the first test without a parachute, 0.15 grams of black powder energetically deployed the nose cone. But when we add the parachute, going to 0.3 grams of black powder, there was no deployment. The shear pins didn't shear. Matter of fact, it actually took 1.3 grams to get the same energetic deployment that we had with 0.15 grams and no parachute. So it takes about 10 times more black powder when you add the parachute. So how does adding a parachute so dramatically impact the amount of pressure that's generated? Well, we go back and we take a look at the ideal gas equation and what changed when we added the parachutes. Well, clearly the ideal gas constant doesn't change. The volume does go down a little bit, not a lot. The parachute is mostly air, but the quantity of air in the chamber goes down by the same factor. So the change in the quantity and the volume change basically cancel out, leaving just the temperature to be the one parameter that must have changed. The temperature must be lower if the pressure is lower. Well, what's going on here? Well, if you look at what's happening with the parachute in the tube, the ejection charge fires directly into the parachute, into the chute protector. And so the chute must be acting to cool the gases that are in the chamber and thereby reduce the amount of pressure that's generated. In fact, I did multiple measurements with both different size parachutes and different locations of the parachute. And for the case of the parachute being closer to the ejection charge or for a larger parachute, in both cases, it took more black powder. Now we can quantify the amount of pressure that's generated by going back to the pressure chamber and fill the pressure chamber with a parachute. And when you do that, remember the original test, the mean of the test without a parachute was 28.5 psi, but with the parachute, that pressure drops down to 3.58 psi, whereas the black powder calculator had predicted 6.63. So significant reduction in the pressure with the parachute. And you can actually use that amount of pressure that we measure with the parachute and work backward through the model to calculate the amount of energy that's absorbed by the parachute and show that about 90% of the energy when the chamber is filled with the parachute is absorbed by the parachute. I also did testing with a piston, and sure enough, a piston requires about 40 to 50% of the amount of powder that was used with the chute protector. So it does require a significantly less amount of black powder when you use a piston. Now, what's interesting about a piston when you model it is that the pressure that's generated is actually less than the pressure that you get when you don't have a piston and there's no parachute. And the reason for this is because you're heating a smaller volume of air. You're heating just the volume of air that's under the piston. And that results in a lower pressure. So the reason that a piston works then is because it isolates the ejection charge from the parachute. And so the temperature and the pressure is actually higher. Now, the downside to that is that initial pressure and temperature before the piston moves can be very large. And a dramatic demonstration of that is shown in these photographs. First case is the case without a piston. It took 1.9 grams of black powder in this particular deployment fixture to deploy the parachute energetically. But when we add the piston to that chamber, it only takes a gram of black powder to get that same energetic deployment. But you can just see the temperature of the gases as they exit the tube when the piston is in place. Okay, so a rocket can fail if you use too little black powder, but it can also fail if you use too much black powder and it damages the airframe. And at this point, we don't know how close to the, in this case, 1.9 grams is to damaging the body tube. So the way we'll determine what the upper margin is to continue to increase the amount of black powder we use until we in fact damage the body tube. And in doing that test, starting with the 1.9, then going to 2.5 and 3, there was no damage to the body tube. Got to 4 grams, and this happened. We had a complete failure of the body tube. And what's interesting about this failure is that the body tube failed, but the shear pins didn't shear, even though the shear pins take less force to shear than it takes to damage the body tube. Now, the most plausible explanation of this is that it takes about a millisecond for the shock wave to travel from the back end of the tube to the front of the tube. So what probably happened was the body tube failed before the shear pins were able to shear. Now, that particular fixture was not fiberglass. It's just a phenolic tube. And with the phenolic tube, in this case, we saw about the failure occurred somewhere between 3 and 4 grams. So we have somewhere between a 1.5 and a 2x safety margin. Now that's not a huge safety margin, but had this tube been fiberglass, it would have been much stronger, and you probably would have had more than a 2x safety margin on the upper end. So that's you probably have a pretty good safety margin with a fiberglass tube. Okay, so now we have everything we need to create the new black powder calculator model. And we're going to start by using the ideal gas equation with the heating of the air included. And we're going to multiply that by the cross-sectional area of the body tube to calculate the force that's generated by the black powder. And then we're going to equate that to the force that's needed to shear the shear pins, including a safety factor that's needed to go from a marginal deployment to an energetic deployment. And when we do that, then we're going to solve that equation for the mass of the black powder. Now, that equation is also going to include a factor that accounts for the absorption of the energy by the parachute, and we'll talk about how we got that function in just a minute. Now, that's a complicated equation to solve, but the MathCAD symbolic engine was able to solve it, and that results in a closed form solution to the amount of black powder that's required, which is what we need for the calculator model. Now, to calculate the absorption by the parachute, what I did was to use an exponential curve fit to the deployment test data. And that allows the model to account for the size and the location of the parachute. Now, again, this is an engineering approximation, but it allows the model to account for the energy that's absorbed by the parachute. And when we do that, we get a model that agrees very closely with the test data for the 2 different sizes of deployment fixtures that were used and various sizes and the locations of the parachute. Unlike the old black powder calculator model that didn't take into account the heating of the air and it didn't take into account the energy that's absorbed by the parachute. Now, since then, I have actually flown both of the rockets that had originally experienced deployment failures, TR1 and VTS1, a number of times. And the amount of black powder I used, which was recommended by the new model, was twice what I had used originally when I had experienced the deployment failures. TR1 has flown an additional 2 times with the increased amount successfully, and VTS1, which is my vertical trajectory systems rocket, has flown an additional 11 times successfully. Okay, so summarizing the key conclusions, the exothermic energy of the black powder reaction increases the initial pressure by heating the air. The parachute absorbs much of the exothermic energy and lowers the initial temperature and pressure. A piston isolates the parachute from the ejection charged gases, increasing the effective pressure, and old black powder is not a problem. Recommendations. Well, first would be to update the calculators based on the new model. I need to translate the MathCAD model into Excel so that it's more accessible. And then secondly, ground testing. Ground testing has always been highly recommended, but it's clear that that testing needs to be done with the parachute and the shock cord in the flight configuration because it has such a big impact on the amount of pressure that's actually created by the black powder. Okay, well, thank you for listening. And with that, it's time for questions. First question, won't the parachute slide to the rear during the launch? Well, yes, if the black powder charge is located at the back end and the parachute doesn't fill the chamber, likely the parachute is going to be forced backward. And so in the model, it makes the most sense to use the absorption factor that places the parachute closest to the ejection charge. So you have a more accurate estimate to start your testing. Have you thought about trying to measure the temperature? Yes. So I did think about that, didn't actually do it. I think a thermocouple would respond, the response time of a thermocouple would be too slow to measure the change. I did purchase a IR detector that was capable of measuring up to 700 degrees Fahrenheit. But in thinking about it, if you were to place the IR detector in the chamber, what is it looking at? That's what it's going to measure. It's going to be looking at both the walls of the chamber and the air and the gases in the chamber, and it's not exactly clear how that's going to actually read out because the walls are going to be a lot cooler than the gases. Also, if you put a parachute in the chamber, then that's going to block the sensor. So I think it's something worth playing with sometime in the future, but I didn't do that in this project yet. Next question, is 2x really enough margin on the upper end? Well, yeah, 2x is not a huge margin. I think with a fiberglass tube, you'd have significantly more margin. So, I think that's a pretty good margin to have. It's, I think, better to run with the amount of black powder that you know is going to get a clean separation or deployment than it would running with lesser amount. And I still think that that's, it's got a pretty good margin on the upper end as well. Next question, what was the maximum altitude for the two rockets with the failed deployments? Well, not very high. I think the question was the altitude high enough that that would have impacted the amount of pressure that was generated by the black powder? And the answer, I think, is no. The smaller of the two rockets, TR1 flew to about 1,500 feet, VTS1 flies to about 2,500 feet. So those are altitudes where the drop in pressure would not have a big impact on the pressure generated. I did do testing in the pressure chamber with an evacuated chamber. I didn't have time to talk about that today, but got some interesting results at high, basically simulating high altitude. There's some interesting results that are in the paper if you're interested. What type of black powder did you use? I used 4F GoX black powder. That's what's always been recommended. It's the finest grain of all the black powders. I think some people use 3F, which works well as well, but I used the 4F GoX black powder. Last question that I have, did you use absolute pressure in the ideal gas equation? Yeah, the ideal gas equation, the pressure or the temperature, they use absolute temperature in the ideal gas equation. Yes, it did. The temperature needs to express in terms of absolute temperature. When I gave the combustion temperature of black powder, I expressed it in terms of units of Fahrenheit because for me, it's easier to wrap my mind around Fahrenheit temperatures than I does around Rankine or Kelvin. So, but in the equation, it's actually in terms of the absolute temperature, and then also in the pressure is absolute pressure. Well, that's the end of the questions. Thanks again for listening.